In this video, I'm going to talk about what interfaces are and what's the difference between an interface and a class. I'm going to talk about the question of should a method that takes a formal parameter, should that formal parameter type be a concrete type? Should it be an abstract type? Should it be an interface type? What should it be? But we've used the word interfaces a lot over the last few episodes without ever saying what they are. I want to be clear, I'm not talking about graphical user interfaces, that kind of thing. That's not at all what I'm talking about. In C#, an interface is a kind of type, and it's very similar to an abstract class. And interfaces are always reference types. So let me talk about what's the difference between an interface and a class, and then we'll look at some examples. Right? So you can think of an interface as, well, it's kind of like an abstract class, except that it has no fields, and it has no constructor, and every method in it is an abstract method, and every property in it is an abstract property, and so on. That is actually not how I like to think about interfaces. Kind of a better way to think about it is that classes represent the is a kind of relationship. Right? So if I have a base class person and I have a derived class president, then I can say, well, a president is a kind of person. Interfaces represent the I can provide the services of relationship. So I have a class list, and I have an interface enumerable, which is not a great name. Really, it should be sequence. And it's saying, if I have a list of things, then I can provide the services that would be needed to produce a sequence of things. There's another way to think about interfaces and classes, though. Classes are fundamentally a mechanism for code reuse. When you inherit one class from another, you're saying, I have some code in this base class. I would like that code to be used by my derived class so that I don't have to rewrite that code. Interfaces don't have any code in them to reuse. Every method in an interface is an abstract method. There's no there. There's no code there that you can share. Classes support single inheritance. Every class has exactly one base class. So our president class has a base class person. Our person class has a base class object. Object is the only class that doesn't have a base class. Interfaces support multiple inheritance. I have inheritance here in quotation marks for a reason I'll explain in a minute. But you can have a class that says, oh, I'm going to implement these half-dozen interfaces. I'm going to say this class is disposable. Right? It implements the services that are required for an object that needs to be cleaned up when you're done with it. And also, I'm a sequence of things. And also, I can be compared to things of this type. And also, so you can have as many interfaces as you want. Now, I put inheritance in quotes. In C#, we use the word inheritance to specifically mean the members of one type become the members of another type. And that is true, sort of, with interfaces. If you have an interface that has a particular member and you have a class that implements that interface, then we require that the class have that member. But I usually think of inheritance as a mechanism for reusing code. So that terminology can be a little bit confusing, and that's why I call it out with the scare quotes. So let's, after all of that verbiage, let's just take a look at some examples, and hopefully it will become more clear with the example. So we'll go to Visual Studio, and we're once again in our little example we've been looking at for the last few videos, where we've got a person base type and a change request and that little class hierarchy. So an interface is declared very similarly to how we declare a class. You have the word interface, and then you have a name. The name almost always begins with a capital letter I. This is waving a big flag that says this thing is an interface. And this is one of the last vestiges of what's called Hungarian notation in C#. I want to do a quick digression on Hungarian notation because that term will probably come up in your later programming career. Hungarian notation is a convention for encoding a fact about a thing in its name. So for example, if you were writing in a programming language that used Hungarian notation and you saw a field that was named m_c frogs, then your Hungarian notation knowledge would tell you that is a member variable. The m_ would mean member variable, which is what fields are called in some languages. And it contains a count. The C stands for count. And what's it a count of? Frogs. All right, so you would know this thing. I know that it's a field, and I know that it contains a count of frogs. The reason it's called Hungarian notation is first because it was invented by Charles Simonyi, who's a famous programmer. He worked for Microsoft for a long time. He has his own company now called Intentional Programming, which does really interesting programming language research. And also because in Hungarian you end up with these things that you have to decode that are like RGPWCH, and people looked at that and said, well, that looks like it was written by somebody who speaks Hungarian. RGPWCH would be, let's see if I remember Hungarian, that would be a range of pointers to wide characters. So that would be in C++, that would be an array that contained a bunch of references to wide character strings, probably Unicode strings. Do not use Hungarian in C#. It is considered unnecessary to use Hungarian in C#. If you want to indicate that a variable is a count of frogs, then please just call the variable frog count or count of frogs or something like that. Don't have this crazy, difficult to pronounce, hard to read coding convention of Hungarian. It's not considered necessary in C#. But like I said, the last vestige of Hungarian is in C#. Interfaces still traditionally begin with an I, and there's a few more small ones like that. We're not going to talk about type parameters in this course, but type parameters often begin with the letter T for similar reasons. All right. So anyway, let's suppose that we are defining a new interface. I'm going to call this interface ITitled, right? And it will be an interface that has a single property. It's going to be a property of type string. It's going to have a getter, and that's it. Right? Everything in an interface is automatically public, so we don't have to say public. And in fact, it's an error to say public. And everything is automatically abstract, so we don't have to say abstract. It's an error to say abstract. And of course, since everything is abstract, we don't provide any bodies. Right? So it would not be legal to try to put a getter body in here, right? To do something like that. That would be an error. Right? This would say interface members cannot have a definition. So there we go. All right, so interfaces can contain methods and properties and indexers and events. We haven't talked about events yet, but we will. It may not contain constructors. It may not contain fields. It may not contain static members. And like I said, the members are automatically public and abstract. All right, so how is this useful? Right? We have this type that we've defined. It contains a member called title, but there's no implementation of it. So of what use is it? Here's another example, which I've cleverly called IExample. And here we just have a method, a void method that takes no argument. So let's look at how we might implement this interface. The way we implement an interface is we say, well, the interface is kind of like a base type of a class. So I'm going to say, well, I have a class person here. And I'm going to say that person is both ITitled and IExample. So we have multiple interface inheritance here. Essentially what we're saying here is from an inheritance perspective, all of the members of ITitled and IExample are also members of person. Right? So we have a member some method. We have a member title. These must also be members of person. But they have no bodies. They're abstract. So essentially what we're saying is these guys are a requirement on person to implement those two members. So, well, let's take a look. Well, we already have a virtual method. We already have a virtual property title here that matches the signature. It returns a string, and it has a getter. It must be public, right? So we would not be allowed to say private here. If we did that, then we would get an error. Virtual or abstract members cannot be private. If we took the virtual out, then that would be fine. But now this becomes an error saying IPerson does not implement interface member. Person.title cannot implement an interface member because it is not public. So Good error message there. So this guy's got to be public. Now, it doesn't have to be virtual. It could be abstract. It would actually be legal to have an abstract type that implements an interface and provides yet another abstract method that implements that interface method. That's rare, but it does occasionally happen. But anyway, point being, the person class, by dint of the fact that it has inherited from both the ITitled and IExample interfaces, is required to provide public implementations of each member of those interfaces. So here's title. And then down here, here's our implementation of some method. And you'll notice I've used an alternative syntax here. Right? I haven't said public. I have said this method is a void returning method, IExample.some method. I put no public on there. This is called an explicit interface implementation. And this says this method is the implementation of the method that is required by IExample. The interesting thing about explicit interface implementations is they are not considered to be public members of the type. So for example, if I have a method here, m, it doesn't matter what the method is, I cannot call some method on this, because this is of type person. Some method is not considered to be a public member of person. It is only accessible if we then say, well, you know what? The IExample type is compatible with the person type. Therefore, I can make this assignment. And IExample has a some method. And this is useful because sometimes you want to implement an interface because it has a particular service that needs to be provided. But you don't want to pollute, is what some people say. You don't want to pollute the public surface area of your class with a bunch of methods that might not be of direct interest to the developers who are actively using your class for some other purpose. So you don't see this that often, but it does crop up every now and then. And so you should be aware that this syntax does exist, and that you can run into this mistake here where you think, oh, I implement this interface, therefore it must have a public method that corresponds to that interface's members. No, it doesn't necessarily. All right. So what about our derived class? We have a type president that is derived from person. Person now implements two interfaces, ITitled and IExample. Does president also implement ITitled and IExample? Well, it does. That is also inherited. So just as the person class inherits from its two interfaces, the president class inherits from the interfaces on its base type. So anywhere where we need an ITitled or an IExample, we could use a president. We don't have to say that. We could. It would be legal here to say, oh, by the way, this also implements IExample. Right. And you notice we didn't even have to add anything here. The compiler is smart enough to realize, oh, IExample requires a method, some method. And the base type already supplies that. So I don't need to require president to have anything else in here. There is a very subtle difference between this code and this code that involves a feature of C# that almost nobody understands called interface reimplementation. And that difference really is quite subtle, and I'm not going to get into the details of it in this course. Basically, you can choose to restate the interface or not at your whim. You don't have to. You don't have to avoid it. It's really just up to you. All right. So now let's think about our change request base class. It also has a public property on it called title, and so it could implement ITitled. So now we have two types, person and change request, that are completely unrelated. They have no inheritance relationship between them whatsoever, but they both inherit the same interface. They both implement the same interface. Even though the change request class is abstract, it can still implement this interface because it's got this property right here. Also, you notice that ITitled, all it requires is that there be a getter. Here we have both a getter and a setter. And so that's fine. It says, well, I needed the getter. You gave me a getter, so that's good. So let's take a look at a quick example here. Suppose I have a method, just a simple little static void method called printTitle, and it takes as its argument an ITitled. So we've got a parameter here. The parameter is going to have to be of a type that is compatible with ITitled. In here, we can use members of this interface. So we can say, well, there is only one member. It's a title getter, so I can use it here. And also, C# is smart enough to realize every type that is going to implement an interface must itself derive from object, either directly or indirectly. And therefore, I can use the members of object, even though what I have here is not something that sort of implements object directly. So it will allow you to use toString in here, even though that's a member of object, not a member of ITitled. However, members that are not on the interface cannot be called. Right? So for example, we have an implementer property on change request. Change request implements ITitled, but we don't necessarily know that this thing is going to be a change request, and therefore we can't call implementer on it. There's no definition of this on this type. So let's take a look at how this works. I have up in our main method here. We'll just step into it. I'm going to create a person, Eric. I'm going to create a person, Obama. That's actually a president. I'm going to once again create this change request. And now we can call printTitle with Obama as its argument, because this variable is of type person, and person implements ITitled. Right? So it says, I can provide the service that you need. Similarly, request is of type change request, and it also implements ITitled. And so it is also saying, I can also provide the service that you need. The service that you need, that printTitle needs, is the ability to get the title. So if we step in here, then we see we have a parameter of type ITitled. If we point at that thing, it says, oh, that's President Obama. His title is president. You notice that the debugger, again, is smart enough to realize, oh, this is actually the president object that we're passing in. It's not going to just say, oh, I'm only going to allow you to see the title because this variable is of type ITitled. The debugger knows what's going on. All right, and so now we can print out the title. And sure enough, it says president. And we can call toString on this thing. And sure enough, we call our implementation of toString, and it says President Obama. All right, if we step back out of that thing, we can now say, now we're going to do the same thing with this request. So we're going to write out the title of the request, which is healthcare.gov is running slowly. And we can call toString on this thing. And remember, we never implemented toString on change request. So it's just going to say, well, that's a defect fix request. Because remember, its default behavior is to say, what is my type? What is my runtime type? And produce that as a string. All right, so we've seen how interfaces work. But why would we ever use them? Well, interfaces are a form of polymorphism. Class-based polymorphism requires the is a kind of relationship. Right? This, well, I need an animal. You're going to give me a giraffe. A giraffe is a kind of animal. That's great. But very often, what you require is not the is a kind of relationship, but the I can do this relationship. Right? I need something that has a title. I need something that can be treated as a sequence of objects. I need something that can compare itself to something of this type to be ordered in a sort algorithm, for example. So interfaces are super useful for that. And also, more importantly even, interfaces encourage programming against abstraction. An interface basically just says, you know what? It doesn't really matter what the thing is. It doesn't matter if it's the president or a list of things that need to be changed. What matters is I need something that has a title. I'm going to display that title. So interfaces encourage writing methods that only ask for what they need. And if you think back to the dependency injection principle and the interface segregation principle that we talked about before, now you perhaps see why it is that interfaces are so important in these things. The dependency injection principle says, if a class requires a service provided, then you should pass in an object that provides that service and let the class use it. Well, That object could be any one of any number of things. All it needs to implement is the right interface. Right? That interface defines the service contract, right, that the class is going to consume. And the interface segregation principle says if there are methods that are specific to specific kinds of operations, then those should be described by specific types. We should not have a base type animal that has both a give milk and a lay eggs method. Really what we want is interfaces that say, I am a milk producing, I milk producer would be a great name for an interface, and I egg layer would be, or I oviparous, I guess, would be a great name for an interface. And now we can say, oh, we have a bird class and a reptile class. They don't have any relationship to each other aside from both deriving from animal, but they can both implement the oviparous interface. And now they can be used anywhere where an egg-laying animal is required. So how should you use interfaces? It's very similar to my thoughts on other kinds of inheritance. If you expect there to be 2 or more implementations of an interface that are unrelated classes, then consider defining an interface for it. But don't overdo it. I have seen code bases in which there are hundreds and hundreds of interfaces that are all super small and that only have one implementation of them each, right? And you have to wonder, well, why did you go to all the trouble of defining an interface if you were only going to write one class that implements that interface? It seems unnecessary. I like to have methods that take interface parameters if possible, rather than concrete types or abstract types. In fact, that's kind of the order in which I would like it to happen. If you have a method that requires some object to provide a service for it, then it would be nice if that was the most general thing possible, so that you can pass in as many different kinds of objects as possible. On the other hand, methods that can only take one kind of thing are the easiest methods to test, because you only have to test passing in that one kind of thing. So again, there's always a balance between the sort of testability and knowability of a particular piece of code, and the ability to be very flexible and to accept, to make a method that does something general and accepts a lot of objects in. So try to find a good balance there. So summing up, interfaces, yet another kind of reference type, similar to classes. Interfaces represent the I can do it contract. And interface implementations must be public, or they must be explicit.